responsibility for TWI industrial members in India and in supporting TWI's ambition there. Chris is a material scientist and has spent almost 30 years in R&D career with a global aluminum producer. Technology areas to which he has contributed include corrosion, thermomechanical forming, novel test methods, plant process optimization, joining, and surface treatment. Today, his role is focused on developing technical and commercial opportunities for TWA and its customers around the world. It's my privilege to invite Chris. Chris, now you can please introduce speaker for today, Mr. James.
Thank you, Krishnan, and thank you for the opportunity again. And when you mentioned to me, both Nimesh and yourself, to perhaps consider beginning this session again with somebody from the UK, I thought it was my great opportunity to get somebody who was not from TWI. And today I'm really pleased to introduce Jim. But you will note that TWI is never very far away. And when I talk a little bit about him, TWI will be mentioned as well. It's good background. And before I begin, I just want to say congratulations to India. We had news today that yesterday India actually inoculated 10 million people in one day. And I think that's just absolutely amazing. So I just had to mention that, and well done, everybody. So it's my pleasure to introduce to you James Bell. And James is basically, for me, he's a perfect example of what's starting to happen in the UK and actually globally. He's had a background in many different areas, often for big corporates, also in research and development and consultancy. And it's happening everywhere, I'm sure, but in the UK in particular, the COVID pandemic has actually kickstarted a whole recalibration of engineering resources. And James is a perfect example of that. And, he'll talk about that in a moment. But I think just to begin on that, I would like to say that what's happening is there's a UK-India recalibration going on. And I'm also talking to James about possible collaborations in India. And you know about that, both Nimesh and Krishnan. And we look forward to developing that, particularly as the pandemic gets better. But I first knew James from a company working in nuclear and defense and aerospace. And this was a company called Darkem up in the north of England. And it's great to go and visit Jim wherever he is, because he's always associated with high-end heavy engineering. And he hails from the northeast of England, which it's also great to be with him because he makes my Birmingham accent actually not look so silly. So you will hear him in a moment. He has a real proper Sunderland accent. And in Darkem, he was responsible for much of the welding there in the team. And then we had the privilege of having Jim at TWI for several years. And at TWI, he was one of our leading consultants. He was based in our Middlesbrough office mainly, but he did a lot of work globally for TWI, particularly in training and particularly in inspection. And then more lately, I went to visit Jim at a company called Technip. And this was in the northeast of England, right by the beginning of Hadrian's Wall in Newcastle, right on the River Tyne there. And, Hadrian's Wall was built about 1,000 years ago by the Romans. And Jim introduced me to something called umbilicals in the oil and gas industry. And it was one of the most amazing things I've ever seen in my life. And if ever you get the chance to visit that part of the world, get him to take you to see this machine. I don't even know what it's called, but it looks like an octopus. It's about as big as a 4-story building. And it also reminds you of a helter-skelter. And essentially, it's one of the most complicated engineering things I've ever seen in my life. And that's when I realized just how hard these people work to go and get us something to put in our tanks to make our cars go. And I was just incredibly amazed by that. So where do we have Jim now? We have his vast experience and his knowledge and his expertise in his own company. And this is quite exciting because the future, I think, is in the reorganization of the knowledge base. And it's tending to happen in the UK in SMEs and startups. So I'm not going to go on. Jim is now offering the same sort of services that he once did on behalf of other companies, except he's now offering them much more directly and, interestingly, probably more affordably and more accessibly. And one of the things he's doing is making partnerships. One of them is with a new startup called RNDO. And that is, for next time, we will hopefully talk about that partnership. So without further ado, thanks, Jim, all the way from Singapore at the moment, where he's visiting family. I'll hand over to you, Jim. Thank you.
Oh, great. Well, thank you very much. A bit of pressure now. It's a fairly, a fairly deep, so hopefully I don't let anybody down here. Like I said, this is my accent, of course. So thanks for pointing that out. It's not Sunderland, it's Newcastle. I'll just get back. I'll just get that one sorted though. But yeah, so I guess without sort of burning any more daylight, I can start presenting and we can start going from there.
You can use the share screen button. I made you the host, so
Okay,
you should be able to.
So I should share through.
Yeah.
Right. I'm hoping everyone can see that now.
You need to get your. There's a photo of your letter. Okay. Okay. No, we got it. That's nice.
Great.
Yeah.
Okay. So hopefully that'll come through. So first things first, because it is the thing, the elephant in the room at the moment. I would just like to just to say it. So it's great. Like I said, the numbers coming out of India yesterday are amazing. You know, we're getting to where we need to do. But of course, our company, Carbon Arc, traveling around the world, we also have made this commitment to move and get vaccinated, do tests, keep everybody safe, and keep ourselves safe. So I just wanted to take the moment to say, if you haven't already, please go and get yourself vaccinated when you can, because this is going to be worth it for everybody. I'm currently sitting in a hotel room in Singapore after 15 days in confinement. I don't want to do this again. So let's please, you know, let's get moved on and forward. So as a quick overview, what we're going to be talking to tonight, I'm going to take you over a quick company introduction so you know what we're about. We then have a case study based around Fischer ferroscope testing of super duplex stainless steels, which we'll have a quick look at the problem, the background, and then how we got out of a fairly serious project issue and dealt with our client in a way that we could all move forward together. So we'll go for that. So Carbon Arc Training and Consultancy. Who are we? What do we do? Well, as Chris said, we're based out of Sunderland in the UK. We then have a presence throughout the world at the moment, but our main areas of concern are India, where we have a partnership with RNDO to help give technical support, training, problem shooting, that type of thing. We also have a presence in China and throughout Southeast Asia. We are very lucky to have a team we can call upon who can not only help us deliver high-class technical content, but also deliver in a multitude of languages. So if we ever get back to India soon, you should see things like our training content, not only in English, but in Hindi, or if you want another one, we can have it in Mandarin or Cantonese or Italian and all that type of thing. So it's all about being in a position where we can give training in a way that's easy for the people taking it to learn. You know, you don't have to just speak English. You don't have to speak in that language. We can get to you however we need to. So that's where we are. What type of services do we offer? Well, we try to say no to nothing. So if you come and you want some physical inspection doing or some weld procedures writing or qualified, we can do that. We can also help you review documentation, radiographs. We offer level 3 support on that. A new and exciting thing we're doing is, like everybody sees the potential of, is moving into drones in unmanned aerial vehicles, and how that can help us change the way we maybe get into dangerous areas or improve the quality of inspection. So we have qualified drone inspectors now working with us and offering that. And one thing which is really a passion of ours is the training side of things. So a lot of my life, I spent about 4 years in India going around all the big cities, particularly in the south, running training courses for the Welding Institute. Now we do that ourselves, where we can not only do very similar type of courses, but we try to take it on a little bit more. So what we're doing is maybe a bit of theoretical training, but bolting on virtual reality welding simulations and practical experience in a mechanical lab or things like that, really to take the classroom work on from a very stagnant, boring place for me into something where people can really engage with. Oh, yeah. And then something else which is really important to us is our corporate responsibility. And it's something we're putting a lot of time and effort into. My daughter's 9. And when I said to her, right, we're starting a company, what should we do? She had a very fixed view on what a good company looks like. So she's now our unofficial director of corporate responsibility. And I have given her 500 hours in which she can select different things we're going to do. Now, we kind of split that across a few things, but the hours are unpaid to community groups, STEM organizations, which is a science, technology, engineering, and maths. So what we'll be doing is going into schools, doing mentoring programs for kids. Some of that is directly engineering based to show them a life in engineering and what it can be. And some of it is just kids who need some guidance, need some help, aren't in a good place in their life, and we can just give them someone to talk to and things like that. We're also starting a carbon offset program within the business. Now, I work primarily in the oil and gas industry at the minute. I do a lot of travel. I understand that has an effect on the world. So what we're doing is we're actively keeping a track on our mileage in our cars, the amount of air miles we make, all of our carbon footprint in general. And at the end of the year, we'll put that into a calculator and work out what we need to invest to be carbon neutral. So, and we'll do that all the time. It's a commitment that will come off our bottom line and just be something we do as a company I want to have. So it's important. And of course, then you can find us on our own website, carbonarc.co.uk. If you haven't already, you can get us on LinkedIn. And we've started a new YouTube channel called Carbon Arc Shorts, which is intended to be lots of small videos, maybe directly on technical aspects. So at the minute, we have a heat input video and an equations video on there. But we are also going to grow that to be interviews with people from industry, day in the life of a metallurgist, day in the life of a welder, etc. So people can use it as a very functional sort of I wonder how that happens. I wonder what that's like, type of thing. And if you'll notice here, what the comment on the left, if you go to our website, we have a list of training sources and courses which we can use. When you email us to get information about a course you're interested in, if you use that code number, we'll know you were a part of this this presentation, and you'll get invited to more discounts and things like that. So please make a note of that, get in touch, see where we can get you on a training course, and that should be good. So without further ado then, this case study, this problem I'm going to take you over is a super duplex steel problem that we had a few years ago on a major project. Now, before we start, this is a sort of case review of a live project starting to go wrong and how we pulled it back to get it over the line and make the client happy, get past the contractual requirements and all that. It wasn't done on an R&D activity. So if we were to do it again, we might have done things differently, but this was in the heat of the moment. This is how we hit a problem. We did tests, we moved on, and we got it. So you might look at this chain of events slightly differently, but this is what we did at the time. Now, the problem we had was we had welding happening in 3 different locations to produce an umbilical project. These locations were geographically very far apart. They were in Africa, the UK, and North America. And we had about 2,000 to 3,000 welds per location. And as we started to produce NDT on the completed welds, we found we were passing visual 100%. That was expected. We had very, very few visual failures yearly because of the controls and the amount of training the welders had. We were always passing dye penetrant testing. We weren't seeing any failures in the material, again, which we expect through high control. And our radiographic acceptance on this project was 0 defects. So no gas pores, no cracks, of course, no inclusions. So we were expected to run a slight failure rate, which we saw and was in line with our expectations. But when we started producing Fischer ferroscope tests, we were seeing a pass rate averaging around 50% over all 3 locations, which was a very big struggle for us, and was causing some massive issues. And it was not only costing us a lot of money in rework, but also lost time. Now, the late delivery cost per day on this contract was about $300,000 US a day. So time frame was very critical, and for every failure set us back, pushed us closer and closer to hitting those LDs. So it was something we really had to look at and get around quite quickly. So a bit more of the background on the welding processes and materials and what we were doing. So 100% of the welding was manual TIG welding, GTAW. All of the qualifications were produced for the project and were completed on project material to our clients' project requirements. So this wasn't just standard ASME or British standard, it was ASME plus a list of other requirements. And each welder was qualified specifically for the joint types they would produce in the work. So there was no range of qualifications. If they qualified on a butt weld and they needed to produce a fillet, we had to do 2 qualifications. on every material grouping, on every thickness they would work to, etc. So everybody had been requalified for the job, procedures all brand new, and we had very good faith in what was happening. The material was all super duplex UNS 32750 tube, again, produced directly for the project to order, mainly from Sandvik in Krummatov in the Czech Republic. And they're all small bore tubes. So they ranged from 12.5 mil to 1.5 inch, 38 mil ID, with a wall thickness between 1 to 2.5 millimeters. So these are very small tubes. Umbilicals are made up of not very many tubes, a bit larger than that. And they were delivered to us in 5 kilometer lengths on reels. So when we had a failure, we literally had 5 kilometers between welds, our welds. And now, the Fischer ferroscopes we were using, if you haven't had very much experience with them, are basically made from an iron probe in a plastic sheath, and they produce a magnetic field. And when the AC magnetic field comes close to the part, the ferrite content within the steel increases the voltage level, and the machine reads that to a corresponding ferrite reading. So you can see here, as the part comes closer, the magnetic field gets larger, the voltage goes up, and the reading then goes up. And the way we calibrate that machine is to take a known ferrite sample, add it, touch the probe on the surface of it, and set a reading of the magnetism to a percentage value. Yeah, so, and that's how it works in when we use it in production. We're going to take the probe, touch the sample, and it's going to basically compare the reading we made during the qualification test to the, is it greater or less than that value, and what percentage would it be? For our project, we had to take readings from 3 locations around the OD of the tube. So this is position 1, 2, and 3 on the left, with at least 120 degrees between each position. And then we would take, say, from position 1, the 12 o'clock position there, we would take 3 readings from the weld metal and 3 readings from the heat affected zone. And the average of those 3 readings needed to be between 35 to 65% ferrite, which is the normal acceptance criteria for welds in super duplex material. Now, when we do a test with non-destructive testing, or any test really, we have sort of 4 possible outcomes. So we can have a true positive. So it's an item is flawed, and the NDT method does detect it, and we find it quite all right. And I've colored that green because that's a good position to be in. There's a defect, I can see it. We have a true negative, which is there's no defect, and the NDT method says there's no defect, which is good. We then move into false positives. So I call this a yellow zone because here there's no flow in the component, but the NDT says there is. Now, the reason why I'm saying this is like a yellow, orange, amber type area is in umbilicals, there's a good saying, which is, if in doubt, cut it out. So we don't really live within it. Oh, can we live with it? Just put it in the water, it'll be fine. If there's any sort of reason, so we chop the weld and re-weld it. So false positive is not good, but it's better than the last one, which would be a false negative. So that's where there is a defect and our NDT method doesn't detect it. So we're doing our NDT and we're living within this area. Of course, we want to be in the green, but the convention was, if we're in the orange area, that's okay. We live with it. We move on. We shouldn't get too many of those, but we never want to be in the false negatives. So we were in a position where we had a lot of failures within our production welds, and we weren't sure what was happening. We had welding procedure data and welder qualification data, which said we should be okay. We'd qualified for the item, but we were still not really having good success. And that was adding a lot of time, a lot of cost to the project. So what we started to do was look at, right, what are our possible outcomes here? Why are we getting these readings in production? So the first thing we did was go back to our qualifications and review our ASTM E562 data, which is the point count of the ferrite, which is a reading which we believe should be absolutely correct, because we've cut the sample open and we've looked at it and we say, this welding process on these welding variables produces this value. It's not an NDT test, it's a real countable value. And in all, we weren't seeing an issue. We recounted some parts and we're like, no, these qualifications are correct. We're welding, we should be getting a good value. The ferrite balance was correct. We've got no third phases and no secondary austenite, no sigma, nothing like that. It was all clean. So we moved on to the next thing to look at. Just one reason we could have lower or incorrect ferrite results is we've lost control of our welding process. Either the welders aren't welding correctly or it's not in line with our qualification data. Let's have a look. So we basically did a huge audit of our welding systems, and again, found enough pointers in the right direction to say, we're okay. Our welders are qualified, they're working in line with their requirements. We sent some samples for G48 testing as part of their qualification. We knew they could produce what they needed to do. So that then got us, right, our weld procedures are good. Our welding controls, we believe, are still adequate for what we need to do. Let's look at our materials. Where are we going wrong here? Now, as I said earlier, all of the materials are produced but for order by the mill, and there's full control of that. We know exactly how that material is going to be produced, what it looks like, how it's tested. All that's done in a huge amount of detail before we get it as the umbilical producer. So what's wrong? Quick, have a check, see where we are. Now, the material certs were correct. We did additional tests to make sure the material certs were correct. And everything, again, was fully in order, but we have this very, very high failure rate. So then we started looking at the equipment. Is the Fischer ferroscope in calibration? Yes, it is. Is it in good condition? Because we all know what happens with equipment when you give it to somebody on a work site. It normally doesn't last very long, but no, the condition was new. It was how it was operating. All our tests on the calibration blocks said, yes, this is all okay. And then we did spot checks on the training of all of the operators globally and found that everybody knew exactly how to use the equipment. We could take them through a blind test on calibrating and taking test results, recording test results. We even went to the extreme where we checked that they were able to average 3 result numbers correctly, because we just couldn't work this out. And again, everything was green, everything was fine. So what we then started to do was, right, well, processes are fine, our training's fine, our material's fine. Is there a fundamental issue with Fischer ferroscope testing which is giving us an incorrect value? So what we did is we took a load of different results here. And as you can see, on average, the Fischer ferroscope reading on the small bore materials was quite a long way out from the actual ASTM point count results. And it was worse the thinner the material got and the smaller diameter it got. Now, this is three sort of cross-sectional results I've shown for you here on 1 millimeter, 2.4 millimeter, and 7.1 millimeter thick tube. But in some cases, we were seeing results as much as 30% lower than the actual result. So we were getting point count data at 40, 45%, and Fischer ferrite results from it at between 5 to 10%, which instantly, okay, we've got an issue here, and this is really our issue. But how do we have an issue on a NDT process that our client has deemed we need to do, the industry at large is happy to do as an NDT process to say everything's fine? So going back, we had a true negative. We knew in the ASTM result that was fine, there's no problem. But in our Fischer ferroscopes, we were getting false positive readings. Now, to take that on a little bit more, what we did is say, right, we get 3 different operators to test the same components. And what we did is we got 20 different samples and did a bit of a round robin. And as you can see here, the range of readings we were getting was just all over the shop. We were getting a range which was way outside of what should be acceptable for an NDT method. So what was happening? Well, we started to get to the point where I was like, okay, how are we getting these results? So on a calibration block, you bring the probe down to the surface and it takes a magnetic reading and you get a result. That works. That was proven fairly consistent. But when we do it on a thin wall tube, we bring the probe down. In our area of test, a lot of the time is empty. There's not a lot of material in it. Okay, that's a potential. And then what we also started to see was if it was hard to get into and the operator moved the probe left and right as they took the reading, it really threw the data out and to some were passes, some were fails. We saw that if we brought the probe down at one angle, it would fail, but if we moved it, it would become a pass. So it's really starting to say, all right, we've got a fundamental issue with the way this NDT method has been applied. Now, when we went back, of course, looked at the equipment, got as much data as we can, we could see that the scopes came with a conversion chart. Now, this was to take your reading and then have a percentage increase on your reading, basically on wall thickness and diameter of tube. Now, one of the main issues for us here was all of the conversion charts are based on ferrite number, not ferrite percentage. So for our project, we had to have a ferrite percentage pass or fail, not ferrite number. Now, there was a lot of discussion at the time around how do we convert a ferrite percentage number to a ferrite number, and it became a big bone of contention, not just internally within the company, but also between us and our client. Because how do you decide what a ferrite number is if you don't fully understand, a martensitic structure in your material is going to throw that out, what the phase balance is like, all that type of stuff. So very quickly, these conversion graphs became really a non-starter for us, and we couldn't apply that. What we also found was when we look at the heat affected zones that we were testing, when we bring the probe onto our weld, our heat affected zones measured from our PQRs were no bigger than 1.5 millimeters wide. The probe location at best was 7 millimeters away from that. So most of our probe was actually sitting in parent material, and we were never testing heat affected zones. Something else, just saying, like, is this process really what we want to do? And then out of luck, and it really was luck, and this is the power of Googling, and something I'd say we should always do as much as possible, but always be careful about what you find on the internet. Not everything people say is the right answer is the right answer, but there was an AWS journal on the predictive measurement methods of delta ferrite in stainless steel. And what it did, it basically compared data from 1920 all the way up on lots of different equipment for determining ferrite results. And 3 things came out of this AWS journal, which were kind of a lifesaver to us and allowed us to really say what we're saying is real. It's not the way we're doing it. We're not taking our results and twisting them to fit a narrative we want to get a pass, but somebody else has seen this independently. So first one was that the Fischer probes produce an inspection bubble of about 10 millimeters cubed, which we could see because we did get a difference between thinner and thicker materials. It also said measurements needed to be done on a flat surface and couldn't be done on small bore tubes. And then the last one was that, and it was something we hadn't accounted for, and it was actually the degree of surface roughness drastically affects the results we get within the output of the result. So if you have a polished tube, say an incoming goods tube, and you test it, you'll get one result. If you weld it and the surface becomes tarnished or oxidized, and you test it again, you get a different result on the same component. Even if you take some Scotch-Brite or some emery cloth, scratch the surface, you get a different result. Now, when you've processed material through a factory, the surface roughness is not the same to where it began with, and that was a massive issue, and really said to us, look, we have the evidence now to move on to our client and ask if we can basically get rid of this test. So that's where we came to. So our conclusion was really when we looked at back to our 4 detection options, was we were in a false positive area, but unlike normal, we couldn't accept the false positive because our downtime was too high, the cost was too much, and really the impact overall on the project was not where we could accept that to be, which was a big change for us at the time, because for the 5 years previous to that, we had been fairly happy just to cut out and run and not really think about it. So what did we do? How did we get out of this situation? Well, we went to our client, we wrote a deviation request and said, okay, Fischer ferroscope allows a good assessment of in-process welds. but it can't be applied to thin wall tubes. And it's definitely an issue when we're looking for ferrite percentage rather than ferrite number. Because the correction factors can't be used, and we can't use these tests to produce a definite pass or fail on a weld. We can use it if we want to have a rough idea about where we are, but not to say it's a pass or a fail when all of our NDT methods and all of our controls say that weld is a good weld. So we use it just to see if it's roughly where we need it to be. What we ended up seeing as the close out with this last point was what we'll do is for every procedure qualification we do, from the same location, we will take ASTM E562 point count data and Fischer ferroscope, test it, and produce a tolerance on the Fischer ferroscope reading. We got to a point where we ended up agreeing that the Fischer ferroscopes could be down to 25% reading and still be okay. Once it got below that, we'd need to do extra tests to make sure it was okay. Now, we believed that was a good way out. However, I could probably write a whole different presentation on how to deal with a client's expectations and maybe the way that clients write specifications potentially to get deviation requests so they can ask for something else. That's only my sort of view on it, but it's we got there. We got to a point where we got an agreement, but did it get us into a position where we had a foolproof way of removing Fischer ferroscopes for all projects? No, because our clientele just wouldn't, they needed to see Fischer ferroscopes on a project. But by doing this investigation, by having a clear sort of, right, we need to find out why we're getting incorrect or why we think we're getting incorrect NDT data, allowed us to get to a point where at least we could manage the risk internally and really start to look at upcoming tenders and say, right, what is our risk as we go into this project? If we're being asked to do Fischer ferroscopes on thin wall materials, is that something we want to get out of early in the project at tender stage, or at least building enough tolerance that we can live with any rejects that come out? And that's really where we got to. So like I say, I wanted to take you through where, how we dealt with an issue as we came through a project. It's not an R&D. It would be a great big R&D study, I think. And I think anybody who had the time and the resources to do that, I'd love to help them out, because it's Fischer ferroscope is a good test if it's used correctly and the expectations around the test are correct. You know, don't use it again as a go, no go. Use it as a quality assurance. Let's make sure we think we're in the right ballpark. So yeah, I hope that was interesting. And I'll hand back for any questions.
Thanks, James. I think there are about a couple of questions. First of all, I like an analogy with your false positive and false negative. This is pretty much like COVID, you know. It's all right to have a false positive report where you get isolated and don't harm others, but a false negative, you could ruin a lot of other things. So yes, I think what you shared is quite practical and very, very critical. These are small but really impactful discoveries along the way, because clients mostly do put in requests for certain tests without having a detailed application know-how about the same. For example, small bore, the probe itself would be difficult to get there, and that can create an havoc. And I don't know how many you repaired before you really got to the stage of analyzing it. A lot of cut and repair would have gone in.
We, like I said at the beginning, I've only showed a very small amount of data. Internally, unfortunately, it's not data I have access to anymore, which upsets me a bit, to be honest. So I need to reproduce all these tests again. But as a company, we ended up testing the best part of 4,500 small bore welds in order to really pin down the trend we were seeing. And the crazy thing was, like I say again, don't expect your clients to really always engage with good results.
Yeah.
The answer we got, particularly on the heat affected zone point about the probe being 4 times away from the actual area, when we got the deviation request back, it said, we understand your point, but we still want you to do it. And it was, oh, okay, you're paying, we'll test, but it's not what you want to test. So if anybody else is seeing that day to day, believe me, there is people out there who feel your pain.
Jim, can I ask a general question?
Yeah.
Because this isn't my field at all, really, but it reminds me of aerospace, where I got more experience, and I'm wondering about the tension between individual clients' specifications on how they want something tested and industry-wide requirements, because there's something called NADCAP in aerospace, and the idea was there would be an industry-wide criteria for all kinds of qualifications. And it's been running now for, I don't know, 20 or plus years, and still you get the primes, Rolls-Royces, BAEs, they say, yeah, we're NADCAP, we want you to be NADCAP, but these are our specifications, and they're all slightly different. And I just wondered if it's a similar kind of issue.
Yeah, 100%. The umbilical industry, and I think like all industries really, is still a competitive market. So large companies, and I'm going to say all the oil and gas companies, join together to get some sort of commonality, but then they still want to have a better product than the person next to them. They want to have some sort of sales edge. If everybody's standardized in a way, it would be great, right? I'm all up for standardization. But when you're trying to sell something, you no longer have something extra to sell because everybody's doing exactly the same thing. I guess I don't see that argument, because if we're all doing what's right and technically correct, then that's great. We don't need to add extra fluff to pretend something's better than what it really is. If it's good, it's good. In Technique, especially over the last few years, there's been a very big statement, and it's kind of rang a really big chord with me. And it's basically, if your client isn't paying for it, it's waste. If you're doing extra things that you're not getting paid to do and a client doesn't want, why are you doing it? And for me, Fischer ferroscope in this application falls into that. Is just somebody coming up with something extra, but really it's waste. But yes, it's for all of the people trying to come up with a standardization, I don't think we'll ever really get there 100%, if I'm honest. But for companies and countries who want to really get ahead, I think there's quite a big thing for. I'll use India as an example, because most people here understand in India's we're progressing to really take over the world in some cases. The faster companies internally in India discuss and agree commonality, stop fighting each other over silly little technical points, produce a good basis to then challenge everybody else. I think that's what every industry should be doing in general. It shouldn't be a country by country thing, but it would help. It'll definitely help some countries get ahead. No. Sorry, I'm just.
James, we have a few questions. Can we take them?
Yes, please. I was as I was answering my questions.
James, we have a few questions
well,
in the Q&A session. So can we take them one by one?
Yes, please.
Yeah. So first one is, what was the acceptance range for ferrite content? Is it 30 to 70?
So the normal acceptance range for ferrite content in Super Duplex is about 35 to 65. Once you start getting higher or lower than that, you definitely start to lose the mechanical properties of the Super Duplex. Most steel tube suppliers work on a ferrite content of around, I think the minimum I've seen really as a standard minimum is about 42, 43%. And they're seen quite actively as being on the bottom end because it's built for when you weld it, you lose control of your cooling cycles. Faster cooling is going to give you a bit more ferrite, so it'll drag it more towards an expected 50%. But yeah, I'd say 30 to 70 is too big. There is a lot of discussion on some academics saying even 65% is too high. They would like to see it down more to 60%. But we're talking about very fine numbers at that point. So yeah. Well, if you work on 35 to 65, you'd never be far off most people's acceptance ranges.
Yeah. So there is a question on G48 test. Can you little bit elaborate on that? G48.
Okay. So in my opinion, G48 test for Super Duplex, especially in a welding sample, is one of the best tests, right? So a G48 test, what we do is we produce a welded sample. The designation is ASTM G48, which is the standard it works to. Very basically, what you do is you take your sample of a certain size cut out, put it into a beaker of fluid at temperature, and that could be, normally for a weld, it's 40 degrees Celsius. And it sits within this fluid for 24 hours. Now, the fluid, a few years back, was seen as being the most abrasive, worst case scenario that your weld would ever see in something like an oil and gas environment. And cooking it for 24 hours would give you a sort of what that weld would see in its design life. And if what you do is before you put it in the fluid, you weigh the sample to quite a few decimal points in weight, put it in, leave it for 24 hours, take it out, reweigh it. And if the sample weighs less, you've had some sort of corrosion normally. And that's bad because you don't want your material to corrode. There's a little bit of leeway. It's about 1.5 grams a meter squared because you might lose some dirt or some contamination off the sample. But you shouldn't see any more than that, or something's terribly wrong with your phase balance in your steel. So yeah, it's a great test. It's a very common test. But yet, if you plug in ASTM G48 into whichever standards database you have, it's a really simple. I like the ASTM specs because they're written in a way where you can just follow them through and go, oh, okay, that's what I'm doing. That's how it goes.
Yeah.
Yeah.
So
hopefully that works.
I think on Any change in ferrite reading in 4 o'clock position?
Right. So, yeah. And this is why, so of course it's all on position of how it was welded. And you see a difference between manual welds and orbital welds. So a manual weld on a small bore sample, you may do it in 3 sections as a minimum normally. So as the welder comes on his good hand, he might go from 6 o'clock position to 12 o'clock in one go. But as he comes round on the other side, he might have to stop halfway to then reset. So I wouldn't think about it particularly as a 12 o'clock, 1 o'clock, 4 o'clock position. I would think about it as where is the most heat in the part, which is why we think about your clocks of positions. But yes, you do get different ferrite readings throughout a positional test, depending on the heat and the cooling rate that you'd seen. And this is why most of the standards say take from those multiple points. The most often one is those 3 positions around the circumference on the small bore. The bigger the pipe gets, you may take it from multiple more positions around it. But yeah, you're going to see a good range.
Okay, and there is a question on if you flush grind the weld,